Mike.
I'm gonna have to use the mic.
Oh, you don't?
I'm assuming you guys can hear me because.
Is that not many people have used GCHP yet. So we expect there to be many different issues that you all run into when you run it on your own system. And we expect that some of these will be common. And so we encourage people to share what they find by both contacting us, and our contact info is on the GCHP home wiki page. And we also have a page linked to there called Troubleshooting GCHP, and we welcome you to create a wiki account and actually add your own information. We would be so thrilled if you do this. So we have to wrap up now, but GCST will have office hours the next hour and a half over at the end of the poster hallway, and also tomorrow from 1:30 to 3. So please feel free to come. We can help you continue to get set up with GCHP, take you through the steps, answer any questions you have.
Yeah,
Thank you.
We're all here through the end of the the weight, so.
All right.
Okay, good afternoon. Welcome to the session of Transport, Sources, and Sinks. We have in total 7 talks and 8 posters. The first speaker is Clara Orby from NASA GMAO.
No, that one, the one right there, closer to me. No, this, I'm sorry.
Okay, we're getting started.
Thanks.
Excuse me. Yoink.
You're just gonna let me know. Do I start? Oh, okay. So today I'll be talking about the impact of the large-scale transport properties in some of the new GMAO forward processing fields. So this is work that I primarily did with Andrea Malad. And so Andrea yesterday gave a presentation where she introduced the new FP fields that that the GMAO has available to constrain some of these geochem simulations. And so basically the question here is, how does the large-scale tropospheric transport look different in the old versus the new FP stream? And so just this is a schematic showing that after December 24th of 2016, there haven't been significant model changes. And so as Andrea said, on January 18th, we have this new FP fields available. And so in addition, at the GMAO, we have a specific set of the same FP stream, but not available to the public. So I'm going to be focusing on differences between these two FP fields, here I'm referred to as FP1 for old and FP2 for new, in order to maximize the window over which I have both streams available. So the simulations I'm going to be using are 8 simulations using the GEOS CTM. This is also an offline model analogous to GEOS Chem, constrained both with the new and the old FP fields. I'm going to be looking at a whole suite of idealized tracers. These are tracers that have zonally uniform prescribed concentrations, tracers that have only concentrations prescribed over land, a stratospheric source tracer that is fixed to an arbitrary concentration above 80 millibars and then can be regarded as a measure of strat-trop exchange. And I'm also going to be looking at somewhat more realistic tracers that have a more realistic distribution of emissions and treatment of deposition. So just to recap from Andrea's talk yesterday, some of the large-scale flow differences that we see. So this is the zonally averaged pressure latitude distribution of changes in the meridional wind, which we're using here as a proxy for looking at outflow in the upper troposphere, or a proxy for the Hadley circulation. And so what we see in the new FP is we see a weakening in the upper tropospheric meridional component of the flow. And so this is roughly about a 30% reduction or weakening in large-scale Hadley circulation. And so in addition to those large-scale flow differences, we also see differences in the parameterized convection. That's what's shown in the top panel. So that's a map of the lower tropospheric parameterized convective mass flux. So we have weakening in the tropics, increase over the mid-latitude oceans. In the bottom panel, consistent with these changes and perhaps in response to them, we also see an increase in PBL height in the tropics and a decrease over the mid-latitude oceans. So the question now is, what impact does this have on the actual transport? So I'm going to be focusing primarily on the top 4 experiments. These are GeoCTM simulations constrained within the top 2 rows, the old FP, then the 3rd and 4th rows, the new FP. These are all performed at C90 cube sphere, roughly 1 degree horizontal resolution. And so what we can do is ultimately we're interested in what is the difference between the old and the new FP, in which case the tracers are subjected to the large-scale flow into the parameterized component of convection. But to interpret some of those differences, because we know that there are differences in the large-scale flow and in parameterized processes, we would like to look at, well, what are the differences that we get simply if we subject the tracers only to the large-scale flow, so the no convection case, and what would happen if we basically compare the two FP systems if we have no convectively processed tracers. So in this case, this is just the transport differences that we get from the large-scale flow. So this is a panel. So in the top panels, I'm showing you zonally averaged pressure, latitude distributions of changes in the distributions of species that have prescribed concentrations in the southern hemisphere mid-latitude. So now I'm going from left to right. So that's southern hemisphere mid-latitudes, southern hemisphere subtropics, tropical surface, northern hemisphere subtropics, and northern hemisphere mid-latitudes. And so what I'm showing in the top panel is the tracer with a 50-day decay lifetime. Bottom panel is the tracer with a 5-day decay lifetime. And so what we can see is overall, we have differences primarily in the tropics. So we have reduced transport to the upper tropical troposphere. We have changes in the subtropics with slight increase in the concentrations of those tracers. And then over mid-latitudes, we see a roughly muted response. And so what we can do is, if we preserve that first row from before, and now we contrast the old and the new FP simulations with what we would expect simply if we compare the case with the old FP in which the tracers were subject to parameterized convection and then they're not subject to convection. So basically what is the transport response mimicked by not subjecting the tracers to the convection? We get a response in the tropics that looks very much like what we're seeing. So that tends to indicate that to us that the differences in the tropics are primarily driven by that decrease in convection in the tropics. And so we can see that still further if we look at maps of the lower tropospheric northern hemisphere mid-latitude tracer in the top left panel, and then the tracer in the bottom panel, where we look at the regions of strong or accumulated tracer in the lower troposphere tend to align with regions of weaker parameterized convection over South America and over the West Pacific. And so finally, just to show you that these actually have some real corollaries, we see these tracers too manifest in radon and in a tracer that's prescribed with carbon monoxide emissions. And so if we look in the subtropics, we see that the differences in the old and the new FP actually are not reflected in the case where we turn off the convection, so something else must be explaining those differences. And so we can get some intuition into looking at that when we compare the old and the FP tracer experiments when the tracers are not subject to parameterized convection. And so one way that we can interpret those enhanced concentrations of the subtropical surface tracers is by looking at the stratospheric tracer, which, as shown in the top left panel, has this nice climatological transport flowing down along these isotropes. And we can see in the new FP, this system is that this exchange is a lot weaker. So I'm just going to skip some of the changes that we're seeing over mid-latitudes. The basic story is that the land tracer emissions increase in response to some increases over convection in mid-latitudes. And just to say that these are relevant to the resolutions at which people are going to be running geochem. So the top panels show the C48 or roughly 2-degree resolution simulations. We're seeing those transport differences manifest in those experiments. So these are transport differences that people should expect to be seeing. And so I'll just leave my conclusions up there, and I'll close with that. So thank you.
Questions?
Oh. Okay. Yeah. Oh.
Questions?
Could you please remind us why we should, what evidence there is that this is a better representation of transport? Just why we should be looking for this?
Well, I never said it was a better representation, right? So I said these are the differences that we should expect to see when we use the new FP to constrain the flow. So I'm making no claims that this is better. This is simply what has happened in response to the changes in moist physics. There have been diabatic heating tendencies in the upper troposphere that have tended to cause these large-scale circulation changes, and this is simply what we should expect to see. But I'm not making claims that this is necessarily better, but this is what we should expect to see.
So a different way of asking the same question, were these changes implemented in order to affect the transport, or were they implemented more because people thought they had changes in the microphysics?
Yeah.
Okay.
Yeah, so this is basically changes, yeah, and as Andrea kind of alluded to before, these are changes. So for example, there was too much ice in the tropical upper troposphere, and so these are changes that were done to the physics, and it turns out that it actually had feedbacks in large-scale flow. So these are always things that are important to keep in the back of mind, and these tracers are unforgiving. They reveal everything, so this is the impact on the transport.
Okay, let's move forward. Next speaker is Seb Eastham from Harvard.
Thank you. All right. Thanks for coming to my talk. I'm Sebastian Eastham, a postdoctoral fellow working with Danielle Jacob here at Harvard. And I'm going to be talking today about, as you can see, the limits on the ability of global Eulerian models to resolve intercontinental transport of chemical plumes. All of this work was done in the old lat-long GSChem, but I've got GCHP moonlighting in the background there, doing a nice CO2 simulation just to give everyone some eye candy. So, intercontinental plume transport, just to give you a quick recap, intercontinental plumes are very narrow layers, usually highly concentrated, that can be evected over thousands of kilometers and over up to 10 days at a time, and which are characterized by high concentrations over time. We have satellite observations of this. This is data from the YASI satellite, or from the METOP-A satellite, the YASI instrument measuring CO plumes. And as you can see, I mean, you could have, if you blinked, you would have missed it. There's a very rapid transfer of CO across, in this case, the North Pacific. That CO remained in a coherent plume. It didn't grow in size, and there was very little change in the column concentration. These are also very concentrated vertically. This shows a different plume being transported, in this case, a high H2O plume on the left. Those are LiDAR measurements showing this relatively narrow, in this case, 1 kilometer thick layer being transported, well, in this case, being observed. A key point in all of this is that we have difficulty modeling these kinds of plumes. In real life, and this is actually not a model simulation, this is a laser-induced fluorescence observation of a turbulent jet, diffusion occurs through molecular diffusion via a turbulent cascade. So you get filamentation off that plume, and then the high surface area which is generated through that allows for there to be molecular diffusion across it at a significant rate. In our models, we don't have this. Instead, we rely on numerical diffusion to do the same job. So our diffusion comes about because of an error, not because of any attempt to explicitly simulate the physical process which causes diffusion in real life and in real plumes. So I'm going to go a little bit more into the dry detail of numerical diffusion now, and just mention that in GSChem, as I'm sure many of you are aware, we have what's called a fourth-order accurate advection solver, TP-core, third order by some measures. TP-core is very good at advecting smooth profiles. When TP-core sees a smooth profile in concentration, it will advect it over time, and we will end up with that same profile at the other end, and that's fourth-order accuracy. But when it tries to advect a steep profile or a high gradient, especially a discontinuity, that will get smoothed out over time. This is a common feature of advection in any Eulerian grid. And actually, TP-core falls to first-order accuracy, so the accuracy is a function of the gradient. This is particularly a problem for plumes because of how plumes behave. If you imagine a plume with some width and some mixing ratio in the center that's being stretched as it travels it's stretched out along its axis. The mixing ratio within that plume actually remains the same. What that means is the gradient across the plume is being increased. That means the plume's gradients are self-sharpening even in the face of diffusion. It will diffuse at first order, become smooth, the plume will self-sharpen, and then it will diffuse at first order again. We have accelerated diffusion in the presence of plumes. You can actually see this when you do some simple two-dimensional simulations. In this case, a 12 degree by 15 degree block is advected, gets stretched out, and gets diffused as it does so. Now, a paper in 2010 set out to try and explain this in a quantified fashion, and they measured stretching using the Lyapunov exponent, basically measuring the rate at which two particles very close to each other separate in a real physical flow. I won't go over the math because it's not very interesting, but you get the idea. They found that the rate of diffusion, measured in this case by an exponential factor, which is applied to the maximum volumetric mixing ratio of a plume as it travels in a simulation, is linked to the Lyapunov exponent, to the rate of flow stretching, as well as to the root of the grid spacing. This means that it's actually worse than fourth order, it's worse than first order, it's half order accurate when trying to simulate plumes. Not a great finding. It also means that the rate of diffusion is a function, as we suspected, of flow shear. But in this case, this was just one plume, it was in 2D, so we said, What happens if we simulate this not in one place, but in 90 different places worldwide? We simulate it in full 2D and full 3D, and rather than taking the 3 simulation resolutions they used, 1 by 1 degree and lower, we instead used a 1/4 degree, a 1/2 degree, 1 degree, 2 degree, 4 degree to characterize the dependence on resolution. When we take those 90 plumes, you can see, in this case, the average Lyapunov exponent along the path of the maximum volumetric mixing ratio in each of those plumes at 3 different resolutions. So here there's 270 points. The key takeaway from this is that, 1, the rate of decay, the rate of numerical diffusion, was proportional. It was a factor of the Lyapunov exponent over time. The second takeaway is that if, as you increase the resolution, you didn't really help yourself. You got a flat decrease in the amount of diffusion, but the fact of the matter is that your rate of diffusion remained linked to the rate of flow stretching. This means not only that we have that connection, but it also means because of the higher Lyapunov exponent that we see at higher latitudes, our model's skill in reproducing plumes is reduced at higher latitudes. We have a locational dependency in our model skill. The second takeaway comes from averaging out the results of all of those 90 plumes that we simulated at various different locations and seeing how the maximum mixing ratio within the plume changed over time. Once again, as the mixing ratio decreases, that means only that we are seeing numerical diffusion acting. We have no other ways to decrease these passive tracer concentrations. In 2D, we can increase the resolution from green 4x5 up to a native 1/4 degree, and we get consistent, if relatively slow, improvements. However, when we try and simulate the plume in 3D and increase the horizontal resolution, as you can see on the right, we really didn't see much improvement. These plumes in real life survived for 10 days coherently. After 9 days, we had 10–15% of the maximum concentration remaining. It had all diffused out, no matter what resolution we picked. So horizontal resolution increase was not only incredibly expensive, it was inefficient at reducing 3D plume diffusion. The conclusions that I've drawn, not only those first 3, are also that we need greater vertical resolution in the model if we're to address this. The problem is not that our horizontal resolution isn't high enough. In fact, in 2D, 1 by 1.25 degree was good enough to resolve most plumes over 9 days. In 3D, we need higher vertical resolution than is currently available if we want to resolve these plumes over the course of the 9-day travel time that we see in the observations. And with that, I'd like to take your questions. Thank you.
So in that last one, was the implication that, on your last slide before this, was the implication that you shouldn't, because there's no explicit turbulent diffusion between Gradatis and Geochem, that we should have actually seen none? The volume mixing ratio should have stayed constant over those 10 days?
I'm really glad you said that because I forgot to. Yes. Yes, in theory, if you're simulating advection perfectly, for example, through a Lagrangian scheme, that volumetric mixing ratio would remain constant over time. Any reduction in this advection-only simulation is the result of numerical diffusion. Thanks again.
Isn't our vertical transport scheme first order accurate?
The vertical transport scheme should be better than first order accurate now, but you're right that it's not particularly accurate. The thing is, we had expected that vertical transport would be slow, and so too would vertical diffusion. The interesting finding here was that actually it was starting to dominate. In fact, it's already dominating. As we move from 2 by 2.5 degree and finer, increasing the horizontal resolution didn't help because even that small amount of vertical transport was dominating the total diffusion of the plume.
Is there a way to fix it artificially somehow without increasing the resolution? Some kind of anti-diffusion or something?
I haven't looked into things like anti-diffusive schemes or anything like that. I think that vertical resolution is actually quite a cheap solution. Consider that when we increase horizontal resolution, there's a 4 times increase in computational cost, plus you probably want to halve the time step, so it's 8 times. When you increase the vertical resolution, it's a 2 times increase if you double it, nothing else, because your time step is very unlikely to be dominated by the vertical rate. So actually, I think that vertical resolution increase, even beyond what the meteorology gives us, might be the most efficient fix. Matt?
Do we need real meteorology, or can we just do it by interpolating the fields into higher vertical resolution?
It's an excellent question. Sorry, Randall.
Could any of these findings have been exacerbated by regridding
I think that the regridding from the cube sphere to the lat-long grid will introduce unnecessary diffusion or extra artificial diffusion, but I don't think we would expect to see an exacerbation in terms of the resolution dependency as we went from that original first regridded data up to then coarser, which is how we did it.
Okay, we have to move on. Sorry. Next speaker is Lee Murray from
So over the past 4 decades, our community has developed this incredible observation network dedicated at characterizing the 3-dimensional composition of trace gases in the atmosphere. This includes the tens of thousands of ozone sondes that have been taken since the 1970s, the intensive but sporadic and somewhat limited in geographic distribution intensive field campaigns, and then the relatively non-biased frequent sampling of key species on commercial aircraft since the mid-90s. But despite all of this tremendous amount of data from which a tremendous amount of science has been done, it's still ultimately fairly sparse. And I suspect that my PDF got loaded instead of my keynote. But this was a little animation showing a relatively highly sampled day. You see some mosaic aircraft flying to and fro the continents. You see some balloons go up. And then you saw 3 of the ICART aircraft sampling around Eastern North America, but ultimately missing large amounts of structure in the underlying ozone field here in the animation. So in geochem, that's not a problem because that's our bread and butter. We can just fly a plane with our plane flight diagnostic through the model, sampling, and do lots of great science, both to better understand processes in the atmosphere, but also better understand to evaluate our model. But for all of the growing number of global Earth system models and climate models are beginning to embed reactive atmospheric chemistry within them, they don't have that luxury. They make their own meteorology. There's no direct matching in space and time between the observations and the measurements. So some of the questions are, well, because they end up comparing to these observed climatologies of the observations, how appropriate are they in aggregate in order to compare to the background concentrations in the atmosphere? So luckily, Geochem can come to the rescue, and we set up a sort of Aussie type experiment where we treat Geochem as truth. So first, we ran Geochem for a decade, where we are sampling along every single flight track and sonde from the during this period that I could get my hands on, and I refer to that as the CTM-like sampling. Then we degrade the model output into a decadal monthly mean climatology and sample it in a way that would be similar to the way that a chemistry climate model would evaluate, which is also not terribly different from the way that we might do, say, our benchmark simulations, and then compare to the actual model output as truth in order to sort of assess the suitability of climatological observations in order to characterize the mean state of the atmosphere. So here are all of the most sampled species. You can see ozone is by far the most. This is all aggregated to the Geochem resolution. These are all of the different aircraft campaigns during this period, but I do have plane flights generated along with corresponding data merges from 1979 to the present that I plan to release to the community, but please contact me if you are interested in those. So here's ozone. This is the way that we typically look at the ozone observations for constraining global models, where we have divided the troposphere into 10 grid boxes by latitude, altitude, and then show the seasonal climatology. So if we directly sample Geochem, that's in the green, we see, as expected, Geochem does a very good job, small mean bias, but overall we capture the vast majority of the spatial and seasonal variability. So now I'm comparing in blue and getting rid of the box and whiskers, so it's not too busy. the CCM-like sampling of ozone in the model. So the fact that the CTM sampling generally matches the CCM sampling means that at least for ozone, the climate models can appropriately compare to the climatology or climatological observations and are getting roughly the same amount of information as we can with our more detailed history. But that doesn't mean that it's necessarily characteristic of the true model state, which is now shown in blue, which is the actual mean, zonal mean over this entire region. And so there are places where biases pop up. For example, the fact that all of these SANs and planes fly in and out of airports or near airports generally. So the mean average is biased, the sampling is biased high relative to the mean. And then there are other places, for example, most of the sampling in the southern hemisphere is in the South Atlantic, where there's a well-known maximum in ozone. So we would need additional observations in Australasia in order to appropriately capture the mean, or at least the subgrid parameterization within this grid box. So we see a similar story for CO. We tend to have a mean bias, but we at least get the seasonality right. And the northern hemisphere is well characterized, but the southern hemisphere has too little sampling, such that the CCM type method is not appropriate. We'd have to have more observations or more years of climatology to compare in order to evaluate those models. One thing that I was particularly interested in is the potential role of plume chasing, which is sometimes a criticism of field campaigns. The fact that we're always going after these elevated interesting features is that characteristic of the background. And was pleased to see that in aggregate, over this decade at least, the aggregated field campaigns actually closely represent the true mean background state of the atmosphere, for a gas at least as long-lived as CO. So unfortunately then for the short-lived species, which are both short-lived and much more infrequently sampled, then that is certainly not true for the CCM modeling, and obviously we have large swaths that we're blind to for evaluating models like GeoSchem as well. Just some things that we're continuing to work on is now, so that was just how sensitive the mean state and concentrations are. Arlene and I are interested in looking at processes, so the sensitivity, this is the sensitivity of ozone to lightning, for example. In the northern hemisphere, the ozone is very, so this would be relevant for, say, tuning lightning, NOx, to mean ozone to infer what the NOx emissions are, but other places it would be only indicative of, say, the South Atlantic region instead of the greater entire region. And we are then lastly also beginning to look at whether or not we can infer long-term trends, which we do statistically see in the model over the full period, but we don't see in either the observations or in the model sampled at the observations. So I'll just leave my summary slides and just acknowledge the, I'm sure, thousands of scientists that have contributed to all this data and be happy to take any questions. So thank you.
Your last slide, the lack of trend that you show in the observations, doesn't that run counter to what Parrish has been arguing, that ozone is increasing and the models can catch it?
Parrish's observations are the surface. This is above Hohenpeisenberg, right?
Well, they're intended to be background.
They're intended to be background, but they are, this is his the surface measurements at Hohenpeisenberg and elsewhere have much more density. This is just when they put the SANs up, and I'm sure Jennifer would have been horrified at this type of analysis because they changed the Hohenpeisenberg standard, the type of SAN. So I know she used to subset this data record as well, but this is very much work in progress. Okay, thanks.
Next speaker is Do Jen from NI NASA Nano.
My work is to use latitude observations measured by NASA aircraft campaigns to constrain the scavenging and lifetime of lat-210 geoscam. Lat-210 is a radionuclide in the atmosphere and produced by radioactive decay of radon. Radon is also a radionuclide inert gas emitted from the Earth's soil and crust. It has a couple of days half-life in the atmosphere. And once lat-210 is produced, it's not a gas anymore. It will attach aerosol, and its long lifetime will allow it to undergo dry and wet deposition in the atmosphere. The beauty of these two tracers is there's not much chemistry involved. So it's good tracers for study transport and wet deposition in geoscam. So the focus of this work is that if we can constrain the emission, the source term, and the wet deposition, which is a major sink term, we're supposed to get a good simulation of lat-210. And the question we want to answer is that if we constrain this from the observation, what's the global lifetime of lat-210 aerosol in the model? So first step, radon emission update and evaluation. On the upper left side, that's the default radon emission in the standard geoscam. And on the right, I have this radon flux map published by Kai Zhang in 2011. You can see there's a lot more details and regional variations in this new radon flux map. And actually, when I plug this in, it's resulting to much better agreement between the simulated and observed surface radon concentration over 15 surface sites around the globe. A few words about wet scavenging deposition equations. So these three equations are actually the bones of the wet deposition scheme in geoscam. So if you look those much closer, you can see, they look similar, and they all have these exponential terms which represent a first-order removal process. And if we break down this process, actually there are two sub-processes in there. The first one is the partitioning of aerosol in cloud water, and the second one is how fast that cloud water can be transformed into precipitation. So the focus of this work is this first process I mentioned, the fraction of aerosol associated with cloud water. So in geoscam, we now have a lookup table for each species, and we'll show in 3 temperature ranges, the cold cloud, mixed phase cloud, and the warm cloud, what are the fraction of the aerosols associated with cloud water. So for lat-210 specifically, it's 100% in the cold cloud and warm cloud, and it's a little bit surprised that in the large scale precipitation is 0 in the mixed phase cloud, and this turns to be the factor we need to improve to match the aircraft data. So here is a list of all the NASA aircraft campaigns we used in this study, and an important step we did was to calculate 5 days backward trajectory for every measurement of this aircraft data, and we sampled the precipitation type and amount along the trajectory, so we are able to categorize this measurement data into different groups that are mostly affected by convective precipitation or large-scale precipitation. So I'm not going to go to details about how to turn the model. I will just throw the result directly. So here I'm showing the average difference between the model result and the observation. So if each of these bars represents a specific wet deposition treatment. So the standard model will give you a little bit overestimate. And so the first step we did was to remove some of the wet deposition schemes in placement by Qiao Wang based on observation of black carbon. So she added the snow and ice phase scavenging. Actually, we think this was a positive improvement for lat-210 as well. But when we add large-scale mixed-phase cloud, the model performs even better. And there's some evidence out there to support those additional removement in mixed-phase cloud. So after that, we have the model scavenging constrained, and we want to compare and evaluate the model performance with some other data that are independent from the aircraft data. So we found a few data sets. This shows the surface deposition flux and surface concentration. And after we changed the radon emission rate and applied the mixed phase cloud, this becomes much better. And same thing here for lead-210 seasonality. We have grouped the surface site into different places, and we show the observations in this black line, and the standard model kind of pick up the seasonal trends, but when we have the emission updated and large scavenging applied, this is much better too. So this is the most important message I want to deliver today, which is the change in global troposphere lead-210 lifetime. So the standard version gives you 8.5 days, and after all these changes, it dropped to 6.9 or 7 days. And a large change we have seen is in this high latitude range, it dropped from about 14 days to 8 days. So a suggestion I have here for those of you who are working on soluble aerosols, and if you haven't, please go back to look at the scavenging coefficient in the model, see if they're 0 or not, and if it is this probably going to explain your overestimation in high latitude region. So I'm going to left my summary slides here, and I'm happy to take any questions you have. That hotspot, there are some explanations for that. One is the soil has much more rhenium concentration, and there's some, the fertilizer used here probably has higher rhenium concentration. So that's the explanations have been read.
How sensitive are you to any seasonal changes in radon effects, like due to snow cover or ice cover, like in high latitudes, because that's where you see a lot of the changes?
Yeah, in the default emission, we reduce the emission by a factor of 3 when the soil is freezed. And in the new emission, we actually, the Kai John's paper actually based on the flux measurement, but it is sensitive to temperature and land cover.
Okay, good afternoon. Today I'm going to talk about some of the results that by using the multiple sensor to constrain the emissions. So this work is in collaboration with Devon's group and also Yuxian Wang's group. So if in the IPCC assessment, we're interested in the aerosol radiative forcing in terms of the different aerosol component. So it's just like we talking about the greenhouse effects, we're interested in the CO2 forcing, but we also want to know not only just the total aerosol direct radiative forcing, but also the forcing as a function of different species. And therefore, we want to know how much emissions there are of those species. So the aerosol emissions actually is very important because the CTM simulations can only be as good as your emissions. If your emission is wrong, then there is an inherent error in our model. And in the past decade, we have seen a lot of the efforts to assimilating solid data and also surface observations to improve the air forecast of air source. However, those forward model simulations normally does not correct emissions. So in other words, any error in the emissions still remains, and this can be a problem, especially considering the solid retrieval of air source is only available in cloud-free conditions, and 60 to 70% of the time, the globe is covered by the cloud, and therefore, if you don't have any air source observations, then your assimilation, although it's running there, but if there are new data, that the impact of assimilation will decrease rapidly, and so in most time, could degrade the air quality forecast. So what we so as you can see, the current framework is try to compare the solid observations with models and then try to do the forecast and validation. So what we try to propose is try to link the solid observations to the emissions using the both forward and a joint model of the GeoSCAM. So here kind of a conceptual diagram. We have building a kind of a framework where we build upon the GeoSCAM forward calculation, and then using our in-house developed radio transfer model that's built upon the VLiDAR, but add a lot of the flavor for air optics as well as the diagnostics, so that we can compute the stock vectors of the radiation, as well as their Jacobians to all the aerosol properties, including all the way to the aerosol distribution and the refractive index. And then we compare that with the radiance, and that's what give out as a differential difference of that. And then based upon that difference and the Jacobians, together with a joint model, then we try to do the emissions. The concept here, of course, there are a lot of huge assumptions here, but we try to think that the first order error probably is the emissions and the aerosol mass itself. So I'm going to show some results here. The first one we started is to look at the April 2008 emissions. We know the emissions declined during that time because Beijing was preparing for the Olympic Games. And you can see on the top left is the 2006 emissions. And then the posterior emissions using 2008 MODIS data, you can see the SO2 emission is slightly reduced. If we use that posterior SO2 emission to do the forward calculation simulation, you can see, and then compare with the OMI SO2, you can see over there this agreement is much better. So we have two independent observation kind of to check that. Similarly, we have looked at the NO2, is the same here. You can see this is the OMI NO2, this is the MODIS constrained NO2, and here is the simulation using primary emission and the posterior emission. Again, much better agreement after using the MODIS invert NO2 emissions. We also looked at the dust. Here is the dust concentration. You can see the default simulation, the dust is too much. And then when you constrain it, you can compare that with MODIS in the dark target region as well as the ground-based observations. Again, looks pretty decent. So we also compare with the MISR aerosol optic depths. And again, those are independent observation validations. Again, you can see over the wide Hook Asia continents, after using the posterior emission, it's getting much better agreement. So put all this together, you can see this Taylor diagram here. You know, those are using posterior emissions. It's much closer to the observations. So once we've done that, we said, well, many of the aerosol precursor emissions, for example, like SO2, once they're emitted, they could be also both in the gas phase and in the particle phase. So from the OMI, we actually also have the measurements of the gas. So what we do is that we say, well, can we use the OMI SO2 to constrain the emissions, and then compare with the MODIS inverted SO2. So we have done that part, and there is a poster here for detail. This should be B19, so I should correct that. So anyway, here is kind of a testimony. We compare the three independent, actually very important independent estimate. So one is the OMI top-down SO2 estimate, another is the MODIS SO2 top-down estimate, and then is basically another one is the bottom-up for 2006. And you can see that the top-down estimate from MODIS and OMI, they all go much better than the bottom-up itself. And you can see most of the large emissions show up in the 2006. actually is largely reduced. And we can see that both from MODIS and OMI. So, so a way forward is that now in the next the next 4 to 10 years, we will have a lot of geostationary satellite, especially that we have high spectral data from the TEMPO and from Sentinel-4 and GEMS. So, and also there will be also another sensor called MAYA, multiple angle, multiple spectral, and polarization measurements. And we have done sensitivity to show that those parametric measurements are actually much sensitive to the aerosol emissions. So nevertheless, I think this is going to be an exciting area in the next coming decade that are using geostationary satellite to constrain emissions, not only on the monthly scale, perhaps even on a weekly scale. Frequent update of the emissions for the air quality forecast and the climate studies. With that, thank you so much.
Jun, how can you separate errors and emissions from errors in chemistry or aerosol optics or aerosol processes?
Yeah, so that's a very good question. So we have done some, there are a lot of assumptions made in here. So one of the key assumptions is that we assume the partition between the scattering and the absorption error, so that ratio itself, the error is much less than the other things. So I think that should be revisited, but for now, that's a huge assumption there. So, and we also consider some model errors there based on the literature, but still very hard to dig into it. But we tried this for many, like for inversion of OMI, we tried it 14 months. Every time we tried OMI using the last month's OMI emission to forecast the next month's air quality, and it's all improved. So I think even the model have a lot of errors. If we have a model every time we use satellite observations to increase, why not? We just try that. So.
All right, good afternoon, everybody. I'm Dylan Millay. What I'm going to be showing today represents work by especially my postdoc, but a lot of folks, but especially my postdoc Hari, my grad student Shin, and a lot of collaborators for the PROPHET study that I'm going to be discussing. So we know that the two-way flux of volatile organic compounds is an important uncertainty in current models, including GeoSChem. And so two questions we're interested in helping to address are, number one, how well can we capture the processes driving that emission and deposition? And number two, are we missing a significant part of the flux? So an important recent advance in this area observationally has been the development of field deployable high resolution time of flight mass spectrometers that actually let you provide a measurement across the whole mass spectrum of organics and with sufficient mass resolution where you can actually assign a molecular formula to most of the detected peaks. So today I'm going to be talking about some observations from my group using a technique called PTR-QTOF, which lets us look at not all, but a pretty wide suite of the VOCs that are of most important for land atmosphere fluxes and atmospheric chemistry. So we were deployed this summer at the Prophet Flux site, which some of you may know, in Michigan, which is a deciduous forest. And this is a mass spectrum from that campaign. And so we detected about 650 different ions, each of which representing an individual atmospheric VOC or fragment of a VOC. And so our measurement strategy here was to spend half of every hour. Basically, one thing I want to point out here is because we're measuring this whole spectrum at 10 hertz, we can actually do eddy flux measurements across the whole spectrum. And so this is a capability that offers sort of our community, offers our community the potential to make some significant strides in addressing those questions I put on the first slide. So we were doing eddy covariance measurements at the top of the tower for the top half of every hour to basically measure net deposition and emission across this mass spectrum of VOCs, and then for the bottom half of every hour, we were doing profiling, vertical profiling through the forest canopy to get independent information on the source sink distribution of these same compounds. And so what we want to do is we want to use that information as a test of how well GeoSChem and other models are capturing this flow of reactive carbon between the land and atmosphere. So, okay, so let's start with one of the sort of immediate findings was that of those 650 ions that we can detect, isoprene and monoterpenes account for about half of the total upward flux that we measure. And so that's, in a sense, good news in the sense that the compounds we think are predominant actually are predominant in terms of what we can detect. If we compare our measured sort of diurnal average isoprene flux in black compared to a high-resolution GeoSChem simulation driven by Megan in red, there's a significant underestimate in Megan, but a large part of that is tied to an associated temperature bias in the model. And so in some ways, this is a basic point, but as a community, we spend a lot of time trying to refine emission estimates based on these types of comparisons, and we're at a point now where, certainly for isoprene and terpenes, where the meteorological and land cover drivers are at least as large a source of error as the emission rates themselves. So for monoterpenes, the model's doing reasonably well during daytime, but there's this kind of interesting diurnal bias in the fluxes in the model. And so why is that? If we compare the monoterpene flux temperature dependence in the observations to the model, that seems consistent. And so what this diurnal discrepancy here is reflecting is actually the fact that the model's not adequately representing the light dependence of monoterpene emissions in this region. So we often think of monoterpene emissions as being purely evaporative and only driven by temperature, but that's not the case for all of them. And so if we plot the monoterpene fluxes at this site as daytime fluxes now as a function of light and temperature, we see evidence for both a light as well as a temperature dependence. And the model's not getting that right based on we're seeing too much emission at kind of low light, warm conditions and vice versa. And so, as we think about how do we speciate VOCs in GeoSChem and how do we lump compounds together, this is the kind of issue we need to keep in mind. And if we represent monoterpenes by one or two sort of surrogate compounds that, like alpha beta pinene, that have no light dependence to their emission, we're going to be changing the diurnal cycle of emissions and therefore their oxidative fate, how much gets oxidized by nitrate versus OH versus O3, which then affects aerosol yields and coupling with the nitrogen cycle. Okay. All right, so what about all these other peaks that we detect? So of the 650 or so ions that we measure, about 420 of them have a measurable flux. Some of that is entirely upward, some of them are entirely downward, but actually the majority have a bidirectional flux. So 420. So GeoSChem has about 30 VOC species, somewhere in that neighborhood. Some of those are lumped. And so the question we have to ask, or that we want to ask is, how, of these 420 ion peaks, how many of them represent compounds that actually matter for biosphere-atmosphere exchange or for atmospheric chemistry? So there's a few ways you could think about that. One is just in terms of the amount of material that's represented. And so what I'm plotting here is the sort of amount of flux that's unaccounted for as a function of the number of ions that you include. And so to account for 90% of the total upward flux that we measure, we only need to include 10 ions. But to get to 99%, you need 99, and then to get up to almost all of it, you need a very large number. And similarly, for the total downward flux, 36 ions to account for 90%, 234 to account for 99%, and then almost 400 to get to 99.9. So overall, basically, we see a couple of things. One is that the deposition flux is carried by a much larger array of compounds. And there's also a very large number of ions with very small individual fluxes. And so the question is, what's their cumulative importance? Okay, so the oxygenated VOCs that we measure, most of them exhibit bidirectional flux. And so what this is showing here is looking at them as an ensemble for the subset that we've sort of quantified so far, and the calibration is approximate for some of these, so this is somewhat preliminary. But we see basically evidence for net upward flux in the daytime, net downward flux at night. And we see that also in the gradient measurements. This is an example for formic acid, where we see decreasing concentrations with depth into the canopy, and then a canopy source during daytime. And it turns out that the model is actually underrepresenting both sides of that bidirectional flux. So here's the emissions, net upward flux at warm, bright conditions, net downward at cooler, darker conditions. And the model is kind of underestimating both sides of, of those gross fluxes. And also, the observed fluxes have much stronger temperature and light dependence than we would predict in the model. And so getting these kinds of process dependencies right is going to matter, for example, for predicting temporal variability or how these emissions might respond to environmental change. So that's I'm being told to stop. I'm at the end of my talk, and I'm happy to stop. I'll put these pictures up here and leave you to figure out what's going on in them, and to take any questions. Okay, yeah. So if I understand what you're talking about basically this idea that isoprene and OH, for example, might be separated in space, and so that would get... Right, so yeah, I mean, that can potentially, I mean, I think for the isoprene story, that ended up being kind of a piece of the puzzle, but not the major piece of the puzzle, right, is my understanding. So yeah, I mean, that's something to think about for really short-lived reactive compounds, potentially. But I mean, the main thing the reason that's more important for isoprene is because isoprene itself is a driver of OH, right? And whereas some of these other compounds, not so much, probably.
Do you think the story is better or worse if you went to an urban environment? So that you had this, there was so many, we could get to 90% from a relatively small numbers, which kind of gave you hope. Do you think if you repeated this in urban environments, is it better or worse?
I don't know, let's write a grant.
Sorry?
I don't know, let's write a grant together. And
I get there's all this money for science.
That's right. It might have to be a UK funder, yeah.
Do oxygenated VOCs have any impact on vegetation, or are they pretty innocuous?
That's an interesting question. I think people like sort of some OVOCs will get sort of assimilated by plants, so they actually get metabolized by plants. In terms of like negative impacts, I mean, some people have raised the question of whether sort of the more oxidized species could cause oxidative stress. I'm not super up on that literature, know like what those impacts are, or how well we understand them, but that's one possibility, yeah. Yep, so we see sesquiterpene fluxes as well as along with the monoterpene fluxes, and we're working on the calibration for those, yeah.
So some people have suggested that one reason ozone in the model is too high at the surface is because there's these missing biogenic VOCs that would react with...
Right, yeah.
Do you pour cold water over that idea based on your measurements?
Well, I mean, so we have OH reactivity measurements at that site by Phil Stevens' group. And the data is pretty preliminary, but we don't have to, we can pretty much explain the observed OH reactivity based on kind of to a pretty close approximation without having to go much beyond the compounds you would normally think of, I guess. I mean, that's, then you can think about that's one sort of metric, right? You want to sort of think about these different metrics that integrate over these different compounds. Ozone reactivity, other things you could think about. Some people were thinking about nitrate radical reactivity.
Thanks, David.
Sure.
I'm going to move on to the last oral talk. It was a post-introduction by Jario Huang from the University of Washington.
So before I get started, I would like to acknowledge my advisor, Liat, and the funding from NASA Ackerman program. So today I'm going to talk about the seesaw aerosols over polar regions coming from the open oceans and sea ice surface. So the motivation for this study is because we found inconsistency between the model and the observations. For example, this figure shows the comparison between the model and the observations of seesaw aerosol mass concentration. So you could see that the GeoSCAM model very often underestimates the seesaw aerosol mass concentration during polar winters. And then the The model study by Chen Jiechen in the previous talk this morning also compares the BRO columns from GOMI and GeoSCAM, and then they found that the BRO abundance is very often underestimated over the high latitudes. So in this study, we implement 2 CI sources of sea salts into the GeoSCAM model, including blowing snow, which is a function of wind speed, snow salinity, snow age, and sea ice concentrations. We also implement separately the frost shower emissions, which is a function of temperature, wind speed, and open list distributions. So let's take a look at the results by adding the sea ice sources into the GeoSCAM model. So the red lines here is by adding the blowing snow emissions into the model. So you could see that the blowing snow simulations has much better agreement with the wintertime seaside aerosol mass observations. And the green line is by adding the frost shower emissions into the model. You will see that the frost shower has smaller influence over the barrel, but it has comparable influence over at alert, which is comparable to blowing snow impacts. That is because alert is located at the regions where the frost shower emission is largest, where there's more open leads and colder temperatures. For blowing snow emissions, it is largest offshore of Alaska, Central Arctic, and near the Greenland, where there's strong winds persistence. So for the open oceans emissions and sea ice sources, they have very different seasonal cycles. For the open ocean emissions, it maximizes in the summer times. And for sea ice sources, they are largest in the winter time in January here. So next, for the Antarctic sites, by adding the blowing snow emissions, which is the red lines here, we also have improved agreements for the wintertime seaside aerosol at the 2 Antarctic sites. The influence of the frost shower over the Antarctic sites is much smaller. That is because the frost shower emissions over the Antarctic is by about an order of magnitude smaller than those from blowing snow. And in terms of spatial distributions, the blowing snow emission is largest at the Ross Sea, Weddell Sea, and coastal regions of Indian Ocean sectors here where there's more strong winds. And then for frost shower, the emissions is largest at the coastal regions of Weddell Sea and Ross Sea, where there's more open leads and cold temperature. We also compare the daily seaside aerosol mass concentrations with GeoSCAM. So the red line here shows the model simulation by including the blowing snow emissions. So you will see that including blowing snow emissions, we can actually capture the seaside aerosol enhancement events on a daily basis. So based on the Institute observation comparison, blowing snow is more likely to be the dominant sources of seaside aerosols in the polar winter. But given that these Institute observations at the polar regions is very sparse, so we also use the Calliope aerosol extinctions over the polar regions to further constrain our sea ice sources of seaside aerosols. So this figure shows the aerosol extinction up to 2 kilometers over the Arctic winter. So you will see that there is some aerosol enhancement in the Central Arctic, but this is not captured in our standard model simulation, which shows about 80 to 100% of underestimates. And by adding the blowing snow emissions, we will actually have much better agreement with the Calliope data. And by including the frost shower emissions in the model, it also helps to reduce the model bias, but it's too weak overall to explain all the underestimate of the model. And for the Antarctic area, you will see that the standard model simulation also underestimate the Calliope aerosol extinctions by 60 to 100%. By including the blowing snow emissions, we actually have better agreements over the coastal regions, but we also introduce some of the overestimate in the southern oceans. And then by adding the frost shower emissions into the model, we actually have reduced the model bias at the region where the frost shower is largest. but it is overall too weak to explain all the model bias in other regions. So to summarize, the blowing snow emissions is necessary to simulate the wintertime seesaw aerosols over polar regions. In the meantime, the frost fire is too weak. And by adding the blowing snow in the geochem, we will double or even triple the annual submicron seesaw aerosol emissions in the Arctic or Antarctic. And there's more details about this study in our recent published paper at ACP. And then for the next step, we are using the Calliope data to further constrain the sea ice sources in the model. And we will also investigating by adding the blowing snow emissions into the model, how it will impact the bromine chemistry. And with that, thank you.
Is all sea ice right for producing sea salt aerosols from snow, or does multi-year versus first year or fresh snowfall?
So there is three different types of salts for the snow on sea ice surface. So one is from the bright upward transportation from the sea ice interior. So if it's like first year sea ice, compared to multi-year sea ice, the first year sea ice will be more efficient in transporting that. And then there's second type of the salt on snow is coming from such as frost fire at the nearby regions, or like the sea salt deposit onto the snow surface. And this too is independent of what sea ice type. But there's not too many observations of what the snow salinity on top of the sea ice available right now. So it's a little bit hard to constrain that. But we are using Calliope data to see if it is different for the multi-year sea ice or first year sea ice. There will be different emission magnitude or something like that.
I have a question for you. How important is the wet scamming for your simulation over the Arctic?
So right now, the Arctic, I was using a version 10 model. So there is not wet scavenging happening for the seesaw emissions happening right now. I would say so, yes, because as shown in this figure, there is some overestimated of the, by adding the blowing snow, we introduced some overestimate of the aerosol extinction, which is probably due to the underestimate of the wet scavenging in the model, because this is a very crowded regions over the southern oceans. And also because the blowing snow particle is emitted as ice particles instead of liquid phases, so it might potentially can act as a ice nuclei in the atmosphere. Yes. All right. Thanks. Thanks.
Okay, let's move to the poster introduction section. All the presenters, can you come up?
Can line up like that way. Whenever you're ready.
All right, let's go. Okay, hi everyone. My name is Karen Yu, and my poster is about the different sources of error in transport, in particular vertical transport, as we go from an online GCM to an offline CTM, where the meteorology is both temporally and spatially degraded, and also about how we might be able to address these errors. So come find me at poster B15 if you're interested tonight.
Hi, we at AER developed a Lagrangian modeling tool capable of analyzing the effects of biomass burning on a given location. The model is two phases. The first phase, which is the backward phase, derives the upstream influence by propagating backward in time. The forward phase calculates chemistry, emission, and deposition forward in time along the parcel trajectories. We'll show a few use cases, as well as a comparison between our model and GeosChem for carbon monoxide. If you have more questions, see me at B16. Thank you.
Hi, my name is Kelsey Larson, and in the spirit of inverse modeling, I'm going to introduce my poster in reverse word order. You think 17B poster by Stop Come Please, Fields GeosFP with interface will that model Lagrangian A, or observations winter of determination age and source and interested are you if. In case you didn't quite catch that, if you are interested in age and source determination of winter observations or Lagrangian model that will interface with GeosFP fields, please come stop by poster B17. Thank you.
I have some questions. So precipitation frequency is more important for aerosols than precipitation intensity and total amount. Is this really true? And can I quantify it? Can I find how much more important each factor may be more than other factors? And can I estimate how much aerosol would be changed when precipitation changed in a long term? So I asked GC on the server, who's the fairest of them all? Please come to find her answer. Thank
you. My student Yuan, his family is going to have a baby, waiting to have a baby this month. So again, I'm presenting a lot of productivities. Anyway, if we want to predict the air quality in Beijing for next month, we probably went up using the emissions we have, probably two or 3 years old. So we are trying to using OMI, considering the emissions in the last month, and then do the forecast for the next month. So we have done the evaluation for 14 months, and it seems to work pretty well. So check out.
Hi, I'm not Chantel Lonsdale, but that's okay because I got the poster number wrong too. I'll just try to focus on the key points here. Ammonia, satellite, infrared, Senex, chickens. Come. Thanks.
Good afternoon. I'm Youfan Chen from Peking University. My job is about ammonia emission from agriculture in China. We use the practical agricultural data to estimate with corresponding emission factors to estimate ammonia emissions, which have distinct seasonal variability. Welcome to my poster number 21. Thanks.
Good afternoon. I'm Arshad Nair from SUNY Albany. I'm examining geochem simulated ammonia concentrations with ground-based and satellite-based observations. My results indicate the model tends to underpredict ammonia concentrations, and we also see a significantly more error in the warmer months. This might make a case for improved gas aerosol partitioning schemes. So come on over to my poster. I'm new to this field, so I will take any and all inputs from you. Thank you.
Okay, thanks, Dylan. So, as Dylan said, I'm Kelly Wells, and I'm going to talk about some work we've been doing at University of Minnesota, looking at what constraints we get on N2O emissions from the Global Surface Observing Network for N2O. N2O, as we probably all know, is a long-lived greenhouse gas and ozone depleter. It's emitted primarily via denitrification and nitrification reactions in soils and in ocean waters. And here I've just listed global annual totals for the different emission inventories that we use as a priori and Geoschem. And they add up to a global annual flux of about 17.4 teragrams of nitrogen for the year 2011. So we're performing an inversion from April 2010 to April 2012, simulating the global network of surface, flask, and hourly observations, which are shown in the map here, and trying to optimize total land and ocean N2O emissions at monthly resolution. And because we know that the inverse problem for N2O is particularly ill-posed, we employ 3 different inversion frameworks to do this. The first is a standard 40 var inversion at the grid box scale, which in our case is 4 by 5 degrees. And the solution I'll be showing today is using 40 iterations. The second is a continental scale inversion, where we just aggregate the adjoint forcing to 6 continental and 3 ocean bands. And the third is applying this new SVD-based approach that Nicolas Bousserez presented yesterday, where we solve for emissions on the optimal subspace based on the information content of our inverse system. And the solution that I'll be showing for this case is using 100 moments. And so we use these 3 frameworks to see how they each resolve the spatial and temporal distribution of N2O emissions, and where we see robust features, what do these features tell us about the global N2O budget and underlying emission processes? So briefly, to go through some pluses and minuses of these different techniques. The standard 40 var inversion, of course, utilizes the existing framework in the Geoschem adjoint, so there's no additional code modifications needed. But of course, when you're trying to resolve a variable at 4 by 5 degrees and monthly resolution at 2 years, you have many more free variables than you do degrees of freedom, particularly for something like N2O. It's also quite slow. You have to do a forward and adjoint run for each iteration. So for the solution I'm showing here, it takes about 120 hours to generate. For a continental scale inversion, this is something that you could do analytically. We don't do it in our case because we want to impose positivity of the solution, so we use the adjoint framework to do this. Of course, when you aggregate, you're subject to aggregation error, and regions are generally determined in an ad hoc way, and this type of framework does not maximize the degrees of freedom of your inversion. Whereas the SVD-based approach can also be solved analytically, which for Nicolas' results yesterday for methane, this is what was done. Though I'll say for N2O, again, in order to impose positivity of the solution, we use the adjoint framework. And to do this, we project the cost function onto the reduced space and then do an iterative minimization. This type of inversion is based on the information content of the inversion, maximizes the degrees of freedom and minimizes the noise, and can be implemented in parallel, so it's quite fast. And the solution I'm showing for this framework takes about 5 hours versus over 100. So we're still kind of working on a posteriori evaluation of our different inversion results, but just to quickly show some comparison, this is for comparison to HIPPO data. The a priori simulation has a seasonally varying bias, particularly in the northern mid-latitudes. So I'm showing here, and I should say that bias peaks in kind of the early fall. So I'm comparing here to HIPPO 5, which was August to September 2011, and just showing a mean vertical profile of the difference between the model and the measurements, shown in the black line for the a priori, and then the different inversions in the colors. So you can see all 3 reduce this bias significantly. Maybe the SVD base reduces it a bit more, but does not eliminate it entirely. Okay, so here are some results that we get for annual emissions for the year 2011. I have the a priori up here on the left, and then the standard continental scale and SVD-based emission results. And then the global annual totals are shown in the boxes, and you'll notice that they're all quite similar. So it looks like the annual global flux is pretty well represented by the bottom-up inventory that we're using. But we do see some fairly large regional differences. Just to highlight a few of those. So over North America, here I have annual totals for the a priori and then the different inversions again in the colors. So we get just modest differences in the inversion relative to the a priori. But in the standard and SVD based case, we get pretty significant difference in the spatial distribution of emissions, where we see a strong increase of emissions relative to the a priori in the US Corn Belt and a reduction elsewhere. So this is consistent with other studies that have shown an underestimate of agricultural emissions in this region. Over Europe, all inversions ramp down emissions pretty significantly. So we are seeing an overestimate of emissions from the European region. And then all inversions do increase emissions in the tropics. And then I'm showing here the example for South America, where all increase emissions. But we do know observational constraints are much lower in these regions, so the magnitude of these fluxes are definitely more uncertain. And then with the time I have left, I just wanted to mention in terms of temporal constraints, which are much more difficult to get than the spatial constraints, we do see at least a robust feature, which is this shift in the seasonality of N2O emissions toward an earlier spring peak in the northern hemisphere. So I'm just showing, for example, here for North America and Europe, a timeline for 2011, where the a priori emissions in black peak in June or July, and the a posterior emissions for the standard and SVD-based case peak somewhere more like April. So this is consistent with the timing of processes such as soil thawing and snow melt, fertilizer application and leaching and runoff, which many studies have shown are really underestimated in bottom-up inventories currently. So that's what I have. Thanks very much.
Can you build it in such a way that the SVD method can give you information in the temporal dimension? Like right now, your SVD is constructed over the spatial dimension, right? You have 100 moments. In space.
Yeah, it does contain the time dimension as well. Yep.
Okay.
Yeah.
Given the observational network, I'm a little surprised that when you aggregate to the continental scale like here, the standard and SVD base actually differ significantly. Is that surprising, or?
They do differ, I think, particularly in areas where observational constraints are low. Yeah, such as like in South America. Oh, you mean for like this plot here? Yeah, so the SVD case, you get much larger changes on a month-to-month basis, yeah. Yeah. I guess I can't say for certain, maybe we could chat with Nicola about this, but in terms of what is more correct, but yeah, potentially with that solution, you're exploring more of the space, and so yeah, you potentially have a better chance of resolving that temporal distribution.
Okay, next up we have Lin Zhang.
Yes, here.
There you are. From Peking University.
Okay, thanks, Dina. So I'm going to present some agent analysis on PM 2.5. Now, our motivation is very straightforward. North China is one of the regions with highest PM 2.5 pollution now around the world, and also is one of the most populated region. So what we interest is, with the help of agile method, what can we learn on the sources and formation process of the PM 2.5 over this region. So as introduced by David Hansey or from Kevin Bowman's presentation yesterday, Agile provide a very powerful on the estimating the sensitivity. And this gives us a very nice way to track the pollution. Now, for example, if we set a target, for example, the black carbon concentration on a specific day at Beijing, then the Agile sensitivity can calculate the back trajectories to tell us where and how much the pollution is coming from. So the model we are using is a quarter degree nested model. Now, one issue is from the observations, there are very strong sulfate formation in winter over this region, and the models do not capture it. So we test a possible chemical pathway, aqueous phase oxidation of dissolved SO2 by NO2. And we see by adding this reaction, the sulfate formation in geoscan increased by 70%. And also we assume that the oxidation by H2O2 and ozone not only occur in cloud droplets, but also on decreasing aerosols. And together, these two reactions double the sulfate concentration in wintertime of this region. Well, there are still some debates on how important of this reaction is because it's highly dependent on aerosol pH. So our implementation here is rather arbitrary because we set a fixed aerosol pH of 5.6. But nevertheless, with these corrections, the model is able to capture the high sulfate concentration as well as other chemical composition of PM2.5. Now, with the Agile, this sensitivity we can get, we also interpret it as a source contribution. Now, this is for PM2.5 at Beijing for the January monthly average. Now, it shows the sources contribute to Beijing from different emissions sectors, from residential to agriculture, and also further separated by different chemical species. Now, we can see the majority is coming from residential emissions, accounting for half of the PM2.5 pollution in Beijing, and also it's mainly coming from organic carbon as well as anthropogenic dust. By the way, we also implement the anthropogenic dust, also the primary PM, that's the emission estimate from Tsinghua University, and that's mostly the magnesium and calcium emitted together with black carbon and organic carbon, and we can see it's a quite important contributor. And also we see agriculture ammonia account for 13%. That's associated with formation of ammonia sulfate and ammonia nitrate. And also we can further apply this method not only at Beijing but to other mega cities over the North China Plain. And here shows the source attribution maps, and also the bar shows integrate over each region and each province. And the key message here is that we can see among the different cities there are very strong regional pollution influence, and with the Agile method, we can quantify the local versus regional transport influence. Okay, so now I show that with the Agile method, we can get very nice pictures on the source sensitivity maps. But they are associated with a variety of uncertainties. One large uncertainty is coming from emissions. So we hope to move one step further using available observations to improve the model emissions. So the measurements we have is from Chinese Environmental Protection Ministry, and there are surface monitoring sites measuring PM2.5 as well as SO2 and some other chemical species. So with the Agile, we can set up the data assimilation system to assimilate those hourly measurements to the model to improve the model estimate as well as source contribution. Now, one very good opportunity to test the data assimilation system is APEC period. This is a November week in 2014. So during APEC is a big economic meeting conference occurred in Beijing 2 years ago, and the government enforced very strict emission controls during this week to reduce emissions and to improve air quality. So it is estimated that emissions during this week is reduced by at least 30%. So we can assimilate the hourly measurements, PM2.5 as well as SO2, to adjust daily aerosol emissions for the APEC period as well as the period before. And the figures shows the model simulation, the prior PM2.5 simulation, as well as the optimized simulation, comparing APEC period as well as 1 week before. So we see the optimized model has better agreement with measurements with the dots. And also, if we compare emissions, for example, the primary PM2.5 emissions, we do see the APEC period is about 30% lower than the week before. So this shows a time series of PM2.5. Black is the observations, and the red is model simulation. For the APEC period is as shown by the arrow, as well as the weeks before. So we do see the optimized model simulation is remarkably well. And also we see PM2.5 concentrations during this APEC week is much lower than the weeks before. And we just show that the emissions is about 30% lower during the week, during this week. But we also see that meteorology variation is very important. So we do see the PM2.5 concentrations at Beijing show a weekly cycle. We can see a few days accumulation and then a sudden drop. This is associated with frontal passage, the frequency of frontal passage. This can be illustrated by the surface pressure. We see the frontal passage that with the high pressure coming from the north. And also we see during the APEC week, the frontal passage is more active. Now we can estimate the source attribution for the high episode during this period at Beijing. And this shows two examples, October 18th and 25th. We can see for the first event, the majority pollution emission is coming from dust. The right panel shows adjunct sensitivity trajectory backwards in time. And we do see dust emission coming from Western China. So, and immediately, so I have to correct my error in speaking yesterday. So that's immediately 3 days ago, right? But we also see for the second case, the majority sensitivity is coming from ammonia emission as well as NOx emission emitted in the past 3 days. So we test a few other episodes, and the source attribution is very similar to the second case. So that suggests a strong inorganic aerosols formation in the fourth season, particularly associated with ammonia and ammonia nitrate. So we are looking for more observations to confirm the model estimate. So with that, I'll stop for your questions. Thank you.
All right, any questions?
Yeah. So the Dyna cycle of model the PM, what's that? The Dyna cycle of model PM is kind of stronger than the observation.
Yes. I know. I think it's pretty well. I mean, you see the correlation is very high, but maybe maybe the boundary condition caused a diagonal variation, but we didn't check. Yeah.
Last question, yeah. In the satellite measurement that generally did repeat the column amount.
Yeah.
Of the species, which are here reflect the emissions in the surface measurement itself, which depend on the weight of the fire. Have you compared with the satellite observations at all?
For this study, no. But that should be a potential future application by adding satellite observations. Yeah.
Okay, we should move
on. Sure. Thanks.
And next up, we have Matt Cooper.
Okay. So NOx emissions inventories still have quite a bit of uncertainty. And we can help constrain this uncertainty by using top-down information from satellite NO2 columns. But to do this requires some inverse modeling. And as we've seen over the past couple days, there's a lot of different ways of doing this inverse modeling. The method that I'm going to be talking most about today is what we call mass balance, which is based off the assumption that the amount of NO2 in a column is proportional to how much NOx is being emitted at the surface. And then we can use a model like GeoSChem to work out what that proportionality is, and then we can calculate a top-down NOx emissions inventory. On this little schematic here, that would be represented by the green line. In reality, the relationship between surface NOx emissions and NO2 concentrations is much more complicated, particularly because of nonlinear chemistry between NO2 concentrations and OH affecting NOx lifetime. So we can do some improvements to our mass balance method by using what we're calling a finite difference mass balance, where we use finite difference to linearize the model around its a priori state to better approximate what that relationship is. There's also have been studies in the past that have used an iterative procedure for a mass balance. And it's been proposed that that can reduce errors that occur due to transport. So what we did in this work was look at all these different flavors of mass balance to evaluate them to try to figure out what the optimal way to do a mass balance inversion for NOx should be. We do this using synthetic observations. We use synthetic observations that we made in GeoSChem by making a known perturbation to the NOx emissions inventory, then running the model and then using that output as our observations. And we do this because this gives us a known true emissions that we can compare our inversions to in order to evaluate these methods. We then use the GeoSChem adjoint as kind of the benchmark to compare these different mass balance approaches to. The adjoint is a much more computationally rigorous way of getting these NOx emissions inventories, but it is also more computationally demanding, so there's a bit of a trade-off there. And so we're interested to see how the mass balance can kind of stack up against the adjoint. In this first test here, we are looking at transport errors in particular. So we produced synthetic observations by doubling the fossil fuel NOx emissions in 4 locations across the globe. What's shown here are mass balance results for January using 2 weeks of hourly observations at 4 by 5 degrees. What we see is if you do a basic mass balance, what stands out is what's often referred to as a smearing error, where NOx is being transported downwind. It's causing us to overestimate our emissions downwind and underestimate them locally. But we see that if you do an iterative approach to your mass balance, after a few iterations, this transport error starts to diminish. And here, in this case, we see about a 10-fold reduction in the error from our inversion after a few iterations. The figure on the bottom here shows that this works for January and for July as well. So iterating the mass balance can reduce this smearing error. But if you compare that to what the adjoint results show, the adjoint still does a much better job at retrieving our true emissions because it's more explicitly taking transport into account as it's calculating the gradients and coming up with its results. So in this case, the adjoint still does much better. We then looked at another study where we looked at a more complex scenario, where now instead of having just 4 point sources that are perturbed, we're perturbing large areas across North America, Europe, and Asia. So that's shown in the top plots. Then we use that to make our synthetic observations. Again, we're using 2 weeks of hourly observations at 4 by 5 here. And so we do a basic mass balance first, and what we see is a basic mass balance can reduce the error in our emissions inventories by about a factor of 2. However, if we do an iterative finite difference mass balance, we can get another factor of 2 improvement in our inversions. It turns out that the iterative aspect of this is most important in January because the NOx lifetime is longer in the winter, so you have more transport, and these iterations are helping to reduce the errors that come up from the transport in the mass balance. In July, the finite difference aspect of this approach is more important because you have NOx emissions from soil, biomass burning, and lightning. If they're complicating this mixture, it's getting more nonlinear, and so accounting for that nonlinear becomes much more important. And interestingly, when you compare our iterative finite difference mass balance results to the adjoint results, we actually don't see a lot of difference. The error values end up being very close to one another. So that advantage that the adjoint had in the simplified case is diminished when things start getting more complex. We tested this using a bunch of different scenarios, and in all of our tests, we see the consistent thing that the iterative finite difference mass balance does as good as, or sometimes better than, the adjoint. We looked at the effects of resolution. We found this was true at both 2 by 2.5 and 4 by 5 degrees resolution. We also looked at some different observational errors. If you add noise to the observations, if you have biased observations, what happens? Well, we still see that the iterative finite difference mass balance and the adjoint are pretty similar. We also looked at the cases that we showed earlier were with hourly observations. So instead of hourly observations, what if you had a synthetic, or what if you had a geostationary instrument, which would give you hourly observations, but only during the daytime, or a low Earth orbit instrument that has a particular overpass time? We looked at that as well using synthetic observations, so by sampling our synthetic observations as if they were being observed by these instruments, using for both of them the spatial and temporal sampling that those instruments would have, and we still see the same thing. The iterative finite difference mass balance is similar to the adjoint. So what we saw, to summarize this up, the iterative finite difference mass balance improved upon the basic mass balance in our studies by about a factor of 2. And while the adjoint method does a really good job in the simplified test at retrieving the true emissions, when things start getting more complex, as you might see in a real-world type scenario where you have real observations, the difference between the iterative finite difference mass balance and the adjoint is actually quite small, which leads us to the conclusion that if you can do an iterative finite difference mass balance, and that offers the ability to estimate top-down NOx emissions in a more computationally efficient manner than with an adjoint, or if you have a model that did not have an adjoint, that you could get good results using an iterative finite difference mass balance. If you are interested in this, our paper was accepted in JGR about 2 weeks ago, so you can check that out there. Thank you.
So I have a question. So one of the differences, I guess, is in the adjointed version, you're minimizing the error-weighted difference, right? And with these other approaches, you're not sort of having that error weighting in the. So is that part of the difference you're seeing between
the sort of error weighting?
Well, when you're doing the adjointed version, you're accounting for the observational error in the
Oh,
sort of cost
yes.
function minimization, right?
Yes.
So is that, and that's not something that's sort of part of the other approaches. And so is that part of the contributing to the different results that you get?
Maybe, I guess. So I looked at, so I should have said that the results that I'm showing here were, for example, not weighting against the prior emissions errors. So no penalty term. And so that has a difference. I guess the observational errors, I'm not sure how that would make a difference, but.
Other questions? Kevin? So the cost function that you defined for the adjoint is global, is that correct?
Yes.
So when you're using an observation, say in Shanghai, and you're trying to minimize, say, the emissions in Shanghai, and you're also trying to simultaneously minimize the emissions in Atlanta, those observations have absolutely nothing to do with each other. And they have nothing, and the two locations have absolutely nothing to do with each other. But you're trying to minimize all of them at the same time. So I wonder if you took and you reduced your cost function to a region that's essentially the path length, the transport path length of the NO2 itself, you might find the adjoint's a lot more stable, might give you superior results, because you're not trying to solve everything at once, but you're only solving that part that's relevant to the emission source itself.
Yeah, that's a good point. That's not something that I've looked at all, but that also might have, that may be related to the first test where we just had the 4 point sources, because things are more kind of like locally constrained, and the adjoint does better in that case. So perhaps you're right that if you were constrained it to a smaller area, that the adjuvant the performance would get a little bit better than the mass balance. But again, it's not something I looked at, but yeah, that could very well be true.
All right, got to move on to our next speaker. Thanks, Matt. Coming up next is Jeff Geddes from BU.
Thank you. So today I'm going to be talking about work that I'm finishing up from my postdoc with Randall when I was at Dalhousie. But yes, I'm at BU now, and just a shameless plug, if all you PIs out there know some clever students that might want to join BU, I'm looking for grad students. So yeah, today I'm going to be talking about the deposition side. So we heard a lot about constraining sources, and now I'm thinking about what happens to these things once they finally leave the atmosphere. Understanding atmospheric deposition, both dry and wet, has a lot of applications in both science and policy, thinking about targets for biodiversity or long-range transport, nutrient management. But the problem is that measuring it is very challenging, especially with dry deposition. I tried doing this in my PhD, and I would say it's prohibitively challenging in a monitoring capacity for sure. And even with wet deposition, which is a little bit easier to measure, the long-term measurements are sparse. And this figure that I'm showing of a map of wet deposition measurements is even a bit misleading because each of those circles represents an exceedingly small point measurement. So I think we're still at a point where chemical transport models, I would argue, are still our best way of getting estimates of deposition over long-term periods of time and over broad spatial domains. So with reactive nitrogen oxides, at least, this all sort of begins with emissions of NOx. They get reacted around in the atmosphere, form other oxidized nitrogen constituents. They can be transported, but are ultimately deposited by wet or dry deposition. So there's sort of an effective mass balance between the emissions of NOx and the overall deposition of all oxidized nitrogen species. So if we can use remote sensing observations to constrain our emissions of NOx, that sort of offers us a powerful constraint on total reactive nitrogen oxide deposition. The study that we did used 3 different satellite instruments. So we leveraged the long-term record from GOM, Skiamaki, and GOM2. This is a very powerful record also because they sort of all have similar overpass times. And we've shown in previous work, and it's also out there in the literature, that these 3 instruments have very nice, continuous, uninterrupted, consistent measurements of NO2 across each instrument. There's no particular bias once you go from one instrument to the other. So it offers us a really powerful long-term record of nitrogen dioxide. We used this finite mass balance approach to inversion that Matt wonderfully introduced, so I don't have to do any of that heavy lifting now. Thank you, Matt. He also showed that there are some other forms of it that produce a slightly better inversion. In our case, we were doing sort of a 20-year simulation, so it's already kind of a lot of computational work. In fact, we had to do 3 20-year simulations because we did one simulation with the prior emissions, another simulation to calculate the column sensitivity to a perturbation in emissions, and then finally a third simulation where we use the top-down emissions to simulate deposition from the atmosphere. This is a map of our global mean NOI deposition over that period of time. And then below it, I'm showing the fraction of total deposition that was from dry deposition. I like this plot because I think it kind of demonstrates the places where dry deposition dominates total deposition are also places where deposition of NOI is very high. So if we rely on our regular monitoring networks, which are sort of easily done by wet deposition, most frequently done by wet deposition, we're missing a lot of the important deposition picture. We can try our best to evaluate our satellite-constrained results with the measurements that are available to us. This is just an example of one thing we did. There's a great data set from the World Data Center for Precipitation Chemistry. So I'm just showing a comparison between this sort of slice in time in our deposition with the available measurements for wet deposition. There's a pretty good agreement, a couple of interesting exceptions, but overall good performance. The wonderful thing about this satellite record is that we have a really long period of time that we can look at. So we calculated long-term trends in global NOI deposition almost for the last 20 years. The hatching in this figure just shows you where the trends are statistically significant. And then I have panels below that show the time series in wet and dry deposition separately for the individual regions that are boxed in that plot. So you see very steep regional trends, although globally the picture is kind of interesting. It's not really, hasn't really changed significantly year over year over those 20 years, although it seems to have potentially peaked around 2011, 2012, and we possibly are in a decline in global NOI deposition, which is kind of interesting. Constraining or evaluating our long-term trends is even more difficult than evaluating the observations with observations from any given year, because long-term measurements that are continuous are even more rare. We did find observations from the networks across North America, some observations in Europe and East Asia that provided us with a long enough record that we could kind of evaluate our trends. But you can see the sample sizes are getting really small, and outside of these regions of the world, I would guess that there might not even be anything that we can evaluate for the last 20 years. The data that we have seems to show that our satellite-constrained trends in deposition are statistically the same as the measurements that were made. But it also kind of speaks to the power of using a satellite observational constraint, because we just don't have any observations from most of the world. There are, of course, a lot of uncertainties that go into an inversion and then modeling deposition. One thing that I thought would be interesting to think about was the fact that the lifetime of NOI is kind of coupled to reduce nitrogen, obviously, through the formation of ammonium nitrate. So given the fact that ammonia emissions are so uncertain, how important is that in our estimate of NOI deposition? So here I'm just showing you the results of a sensitivity simulation, basically, where we are calculating how much of an impact there is on relative NOI deposition given a perturbation in ammonia emissions. So we found that actually over land, a 30% perturbation in ammonia emissions doesn't really impact our estimates of NOI deposition. Although, again, there are kind of some interesting exceptions over Myanmar and especially over the Mediterranean Sea. Presumably those are places where emissions of ammonia from upwind have a large impact on the lifetime of ammonium nitrate, or NOI. So I think this data is useful for a variety of applications. One thing we could do is kind of look at changing patterns in long-range transport, calculating export from specific regions around the world. And by export, I just mean the difference between emissions from a region and deposition locally to that region. So we could calculate how that's been changing around the world with a decline in export from the US on the order of 50%, whereas it's kind of tripled from China, although again, it peaked around 2011 or 2012. Or we could use this data to investigate impacts of nitrogen deposition on ecosystems around the world. So this is just an example. I combined our satellite constraint estimates of NOI deposition with maps of present-day tree cover just kind of explore how NOI deposition has been changing over forests around the world specifically. And again, we see it's declined by about 50% in North America. It doubled across East Asia, but again peaked and has been declining since then. And this decline over East Asia is consistent with other observational studies with OMI more recently showing a decline in a turnover in NOx emissions. So right now we're probably kind of around 2005 levels in that region of the world. So I think satellite observations of NO2 actually provide an interesting constraint on NOI deposition around the world, and hopefully this kind of data would be useful for a variety of applications. And I look forward to discussing some of the challenges and uncertainties with this with you guys. Thank you.
Questions for Jeff?
I wonder whether there are some deposition measurements showing the decline in Eastern Asia.
Probably wet deposition measurements. I haven't looked at the annual average wet deposition measurements available from that part of the world to see if I can identify that turnover. I would expect it to be there, though. But maybe someone else has looked at that data.
Is there anywhere in the world where there's a discrepancy between, I suppose, deposition and in the observations of the model that would be driven by land cover change?
Yeah, that's a really good question. I think it's definitely possible. I mean, especially for dry deposition, obviously. I didn't investigate that. I know actually Caroline, who did work with inferring deposition of NO2 from OMI measurements, kind of looked at a little bit of that. There was definitely an impact in some urban areas that have expanded since the land cover data set that we use in geoschem that would change dry deposition fractions.
All right, thanks, Jeff.
Thanks.
And our next speaker is Jen Chu from CU Boulder.
So hello everyone, my name is Zhen Qu. I'm a graduate student from University of Colorado Boulder. Today I'll be presenting on a decade-scale top-down NOx and SO2 emissions were derived using a hybrid mass balance and Bolivar joint inversion. First of all, I'd like to thank all the co-authors, especially my advisor, Professor Demahanzi. So quantifying the long-term trend of NOx and SO2 emissions at high resolution is important for evaluation of the effectiveness of emission control strategies. The bottom-up estimates have large uncertainties and it takes a long time to compile, whereas traditional top-down estimates are either time-consuming, as in Bolivar, or limited by the nonlinear chemistry and smearing from transport, as in mass balance. Therefore, our first goal is to derive a hybrid inversion method to facilitate long-term inversion of NOx and SO2 emissions. And we have done an 8-year hybrid inversion for NOx, which I will quickly reveal in the first part of the talk. And our ongoing work extends this hybrid inversion to NOx and SO2 joint inversion. And since the chemical interactions among species are important for performing inversion, our second goal is to study the impact of assimilating multi-species observations on the posterior emissions. And to address the correlation among species emissions from the same sector, we also design a sector-based inversions. And I'll go through these 3 goals one by one. To perform Bolivar, we use geochem agent model at NASA China domain and half-degree resolution. In the first stage, we only assimilate NO2 observations and optimize NOx emissions. And for that, we use NASA standard level 2 product. Yet, we recognize that this product is about 50% smaller than domino retrievals in densely populated and industrial regions in China. Therefore, based on the correlation and the differences between these 2 retrievals, our posterior NOx emissions are more robust in Yangtze River Delta, Xinjiang, Ningxia, and Inner Mongolia. Here, I'll introduce the hybrid method. To do that, we need to perform Bolivar for a base year, and that is 2010 in our case. And then we use this 2010 Bolivar posterior as the prior in mass balance, and in order to recover the trend over the years. To evaluate the performance of this hybrid inversion, we designed pseudo-observation test, in which the real observation shown in black line here are the inputs for geochem to generate pseudo-observations, which we use to constrain emissions. And our prior emission showing green line here, it used 2010 anthropogenic emissions for all the years, and it has 50% bias and spatially correlated random noises compared to the true emissions. And our hybrid posterior showing red line here, it has smaller normalized mean square error as well as better correlation than mass balance posterior, which is blue line here. And this magenta dot stands for the Bolivar posterior in 2010. And extending this hybrid inversion to real OMI observations, we got hybrid posterior that has smaller emissions and emission growth rates in China compared to the bottom-up estimates. In the second stage, we extend this hybrid inversion to assimilate both NO2 and SO2 observations. And all of them, both of them are from NASA standard level 2 retrievals. The first step of a hybrid inversion is to perform Bolivar for a base year, and here we are looking at the result for January 2010. The first row here is the difference between posterior and prior SO2 emissions, And the second row is the difference between posterior and prior NOx emissions. And we are comparing these differences when just assimilating single species observations, which is this left column, and assimilate both NO2 and SO2 observations, which is this right column. And here we see that the differences between assimilating single and multi-species occur mostly in low emission regions. And since changing SO2 emissions by 70% only leads to less than 5% changes in NO2 concentration, incorporating NO2 observations does not change SO2 emissions much. On the other hand, increase of NOx leads to increase of OH, which decreases SO2 column. Therefore, we see this NOx increase in India and central China after incorporating SO2 observations into the system. The second step of the hybrid inversion is to perform mass balance to recover the trend. And since we have already done that for NOx, so we are focusing on SO2 emissions, which is the top panel, and SO2 slant column density, which is the bottom panel here. For the emission, this black line is bottom-up make anthropogenic emissions, and the blue and red lines are our mass balance and hybrid posterior. We see very small internal variations in our posterior, and in fact, both of them has less than 10% increase from year to year based on linear fitting. And here for the column, this black line is OMI observations, and the blue line here is geochem simulation using 2010 HTAP anthropogenic emissions for all the years. This means that this trend from this blue line are mainly driven by meteorology, which leads to up to 7% changes from year to year. And this red line here is our hybrid, is the simulation from our hybrid posterior, which has about 35% decrease of SO2 column compared to the one, this blue one simulated using the prior. And in the next step, we'll study the seasonality of our SO2 posterior emissions. Lastly, the sector-based inversion. The motivation to do this is because NOx and SO2 emissions are correlated through the amount of fuel combustion, since each of their emissions are calculated as the product of a species emission factor and the amount of fuel combustion. So in order to incorporate this correlation into the system, we observe NO2 and SO2 column density to optimize 7 sector-specific grid emission scaling factors, including industry, energy, residential, air, transportation, ship, and agriculture. To do that, we wrote adjoint code that calculate the sensitivity of cost function with respect to the emission scaling factor from each of these 7 sectors. And then we apply this scaling factor to NOx, SO2, CO, ammonia, and organics emissions. And here we're showing one of our results. And these are changes of NOx emissions in a 40-var inversion when just optimizing this 7-sector specific emission scaling factor. And the middle one is just optimizing NO2 and NOx and SO2 emissions. And the last one is optimizing both of them. And for this test, we do not include penalty term in the cost function calculation for easier comparison across the methods. And we got 70% decrease of cost function for all of them, but it's clear to see from this that they converge to different solutions. And in the next step, we'll evaluate the posterior from sector-based and species-based inversion through AOD observations and in situ measurements. To sum up, we have developed a hybrid inversion that is more accurate than basic mass balance and less time consuming than 40-var, and we see different trend between column density and emissions for NOx and SO2. Also, assimilating SO2 observations affect NOx posterior emissions, and we got smaller posterior NOx and SO2 emissions than bottom-up estimates in China. We also built up a sector-based formulation to address the correlation among species. And for the details of our hybrid inversion method and our top-down emissions, you can also see this paper just came out at JGR. Thanks.
One meteorological year to get the footprints, right? And then you apply the mass balance. Is there any error associated with interannual variability in meteorology that you would need to be concerned about?
So when you say using one meteorology data from 1 year,
maybe I just didn't understand right. But my
so
understanding is that you're using the joint for 1 year.
Yeah, but for the other years, we're still using those math field data from those corresponding years. So it's like the hybrid inversion says we use 2010 posterior emissions to other years, but for the meteorology, it's still corresponding to those years. Like for 2005, we still use 2005 meteorology data.
You're using the posterior emissions, not the gradients from the...
Just posterior emissions from 40-var. Thank you.
All right, we're on to our last talk before the posters, and it will be given by Yanhong Zhao from PKU.
Yeah.
Do we? Oh, my mistake. Oh, I'm sorry, then I introduced you incorrectly, didn't I? Okay, so our current speaker is Yusong John from UToronto. Great?
Yeah.
Sorry, apologies, take it away.
It's okay. Yeah, that's my presentation. So today I will present some of my work on the multiple species data assimilation on estimate global CO and NOx emissions using the geochem adjoint model. So apparently CO and NOx, they're major surface pollutants. They also contribute in a big part in troposphere chemistry. However, the previous inverse modeling studies focusing on either CO and NOx, they actually have large discrepancy about the emissions estimates when comparing with observations. And part of these inconsistencies are caused by the uncertainties in OH concentration and its precursor, mostly ozone. And Jiang's group actually did some of the tests on CO inversion by employing different versions of OH. And from this bar plot, you can clearly see pretty much in nearly every region, once you employ different OH concentration, the emission statistics are really much different. So to actually better constrain the troposphere OH and its precursor, instead of the traditional inverse modeling by only employing one set of observation, here we're actually using multiple observation by taking the advantage of more and more observations available today. So in my experiments in particular, I was using the MOPID CO observation from Terra, the TESS ozone observation, and also OMI and NO2 from Aura, and also OSIRIS ozone observation from Odin satellite to constrain, say, when you combine OSIRIS and TESS ozone, they're going to optimize the ozone initial conditions. Whenever you put in the MOPID CO, you're optimizing the CO emissions. And for OMI and NO2, that's a product from the NASA retrieval we're using, we're optimize the NOx emissions. So other information for the model setup, we're using 4x5 GeoSchem model and also with the 4D-VAR as our data assimilation scheme. So here are some of our results once we either employ only MOPID or OMI, as well as comparing with the all instrument combined. So from the upper top, you could see our CO posterior emission scaling factor shown here, where pretty much over the northern hemisphere, you're seeing the emissions are scaled up. So this run is in particular a 2-week run in November 2009. However, so these are so the emissions in northern hemisphere are most corresponding to some anthropogenic emissions. But at the same time, you could see for some biomass burning emissions in northern equatorial Africa, the emissions are actually brought down after the assimilation. For NOx, pretty much you see from East Asia, you see some places are with the increase, where some other places are with the decreased emissions. But you're seeing more kind of a decrease over North America as well as Europe. You could also see a high consistency between the one instrument run with the all instrument run. However, such consistency actually are going to vary seasonally depending on the relative cost function contribution, which we will discuss later. So one way to actually confirm these results make sense is we can compare our assimilated ozone concentration with some independent observation. Here we choose Hippo ozone aircraft data, and you could see when we actually brought in TESS and OSIRIS into the assimilation mix, the ozone concentration are effectively improved in most of the bands, except for pretty much the upper troposphere in the northern hemisphere, which we lack of the data in winter for both TESS and OSIRIS. But you see some effective increase by brought in TESS and OSIRIS in that case for other bands. And if you see the ozone concentration distribution, this is the difference between the concentration after the assimilation and compared to the one before the assimilation. And you could see in the UTLS, the concentration of the a priori are overestimating the ozone, which effectively brought down by adding TESS and OSIRIS. In the mid-troposphere, such impact is not that huge, but pretty much you're still seeing some negative changes towards the ozone concentration in those levels. And this is the OH concentration distribution. So you could see the OH changes over the tropics are mainly led to a result of adding the ozone observations in the assimilation, whereas the changes in the northern hemisphere are actually led by the adding either MOPID CO or NOx OMI and NO2 observations. So we do have a better ozone at this point. However, there are still some uncertainties in my study. So again, this is the cost function when you using 4D-VAR. one thing that we need to consider is the relative cost function contribution among different species. And in fact, because, for example, we're running our assimilation using 4x5, for observation like MOPID CO and OMI and O2, their natural observing resolution is much higher than that. In this case, we're employing the super observation. So in this case, we're actually tweaking this R term so that this contribution is actually going to be comparable among different species. And you could see when we scale the gamma towards either MOPID CO or OMI and O2, we see the global CO or NOx estimates actually changes while we are actually scaling this gamma. In particular, in our experiments, the results we've shown for previous slides, we select gamma MOPID to be 64 and OMI to be 16 in particular, so that the global estimates when using multiple species are comparable to the emission estimates when using their corresponding observation only. So that's pretty much the results we have so far. When we're using the multiple species approach using 4D-VAR, we do have some potential to better estimate the CO and NOx emissions by improving the ozone concentration. In the future, like the ADAM campaign, if we have the OH concentration, we also have the opportunity to compare with that one to convince this is the way to effectively improve OH concentration using the multiple species data assimilation. However, pretty much there are also some uncertainties. For example, our NOx emission estimates also rely on this ozone assimilation. And also once in the future, if you add in more observations available, you also complicates the relative interaction between different observations. In that case, we're also dealing with this non-trivial selections on either the assimilation window or the cost function scaling. Also, all current CTMs can do with higher resolution, but when you're actually doing this multiple species approach with a potential higher resolution, you also need to care about the computational cost with using 4D-VAR, because sometimes the computer resources may limit the analysis using a higher resolution. So I will conclude my talk with that. So if you have any question, feel free to ask me. Thanks. Questions? Kevin?
So when you look at the analysis fields minus the observations, and you calculate the residual, so that calculation is a function of time. Mm-hmm. Do you see that they all hit a certain point, or is there certain observational analysis minus ops that remain persistently high even after you do the assimilation?
So this is a global inversion. So if you're actually looking at a particular region, I think that persistence with the consistently either high bias or low bias has its opportunity to stay there for a while. Yes, you're not going to completely correct it that. With some iterations.
Have you analyzed that? Examined it?
No, we haven't done that. Yeah.
Any other questions? So when you use the CO retrieval, do you compare any of the average corners?
Yeah, so we're using the version 7 multispectral version. So to use that and compare with the model, you have to use the averaging kernels. Yes.
All right, great. Thanks. Yeah. Okay, now I think it's the last talk, right? Okay. And Yuanhong Zhao, if I said that correctly, from PKU.
Thank you. Okay, let me change the topic from the inverse model to a simple biosphere and atmosphere interactions, and I will end this section with from your emission sources to my things about the deposition. Okay, I'm Yuanhong Zhao from Peking University, and I want to talk about the responses of surface ozone air quality to anthropogenic nitrogen deposition. And if you are interested in this topic, you can find the paper on at ACP Discuss. Human activities have emitted large amounts of reactive nitrogen to the atmosphere, and this reactive nitrogen will finally deposit to the ecosystems, cause complex environmental and climate consequences. Here, for example, for the ecological systems, for the ecological systems, it will cause damage effects such as this, and oh, thank you. And for the global climate, it will act as nutrients to the ecosystem and accelerates the carbon and nitrogen cycle in the ecosystem, fix more carbon dioxide into the ecosystem, and at the same time release more nitrous oxide to the atmosphere. They are important greenhouse gases. But there are several studies focused on these two areas, but few studies have explored the influence on air quality. So I want to present here is how human-induced nitrogen deposition may affect surface ozone air quality through land-atmosphere interactions. So how can nitrogen deposition influence the surface ozone air quality? I will give the interactions in this left figure. When reactive nitrogen deposited to the soil, it will add into the manure nitrogen, and it will enhance the plant growth and the nitrification and the denutrification processes. The more density plant will emit more VOCs to the atmosphere, but at the same time accelerates the ozone dry deposition loss, and the nitrification and the denutrification processes will emit more NOx to the atmosphere. The VOCs and NOx are important ozone precursors, and the dry deposition is a major pathway of ozone loss. So what is the net effect? To deal with this complex effects, we built a semi-coupled system of geochem with the community land model CLM. We first use the geochem to simulate the atmospheric nitrogen deposition, and then input the nitrogen deposition to the land model to calculate the response of land properties, here represented as the live area index, LAI, and the soil NOx emissions. Then we input the monthly LAI and hourly soil NOx emissions to geochem to calculate the response of surface ozone concentrations. Let us quickly go through the results. Here is the geochem simulated nitrogen deposition. We can see the high values in eastern US, western Europe, and very, very high values in China and India. And over this high nitrogen deposition area, the contribution from anthropogenic sources can count for more than 70 or 80%. We then evaluate the nitrogen deposition flux with the observation of wet deposition. We can see over the North America, Europe, and Asia, they all show good agreements. We then input the nitrogen deposition from simulated by total emissions and the natural only emissions. And then, we then input the nitrogen deposition simulated from total emissions and the natural only emissions to CLM to calculate the response of soil NOx emissions and the leaf area index. We can see that the anthropogenic nitrogen deposition will enhance the soil NOx emission and the leaf area index over the global scale, and the high values are just corresponding to the high value of anthropogenic nitrogen deposition. We must mention here is that the overestimation of the CLM leaf area index. We have tried lots of methods to reduce this overestimation, but the high barriers still exist. And I want to point out the high LAI increment over the Southeast China is partly due to the LAI overestimation. With the enhancement of LAI, the isoprene emissions and the dry deposition velocity also increase, but they show different sensitivity. The isoprene emissions are more sensitive to LAI change at a lower LAI area. For example, in this high value area, we can't see the large increasement of isoprene emissions, but over India, we can see distinct increase of isoprene emissions, but the LAI is not increased that large. The dry deposition velocity shows a different sensitivity. In the dry deposition velocity trend to increase more linearly with increasing LAI. So we think the overestimation of CLM LAI will lead to underestimation of isoprene emission enhancement from the live area index enhancement, but overestimate the dry deposition velocity enhancement due to increased live area index. Finally, by considering the dry deposition, the biogenic VOC emissions, and the soil NOx emissions, we can give the overall effect of the anthropogenic emission, anthropogenic nitrogen deposition on the surface ozone concentration. Here is the result for the North Hemisphere summer mean daytime. We can see the anthropogenic nitrogen deposition increase the surface ozone concentration over the globe, except for some regions with high NOx emissions, and the total enhancements are buffered from the influence from the individual process from the dry deposition. We can see the increase the dry deposition will decrease the surface ozone concentration, but the increased biogenic VOC emissions increase the surface ozone concentration. The net value depends on the LAI sensitivity, and the soil NOx emissions generally increase the surface ozone concentration, except for the NOx saturated areas. Okay, I'll stop here. Thank you for your time.
Any questions? Jeff?
This language change that you're using to compare the effects of with the nitrogen deposition, so I might have missed it. What language change are you modeling? Is it historical or future, or what's the time?
Oh, sorry, due to the time limit, I don't mention that. The land use change is just follow the is just use the CLM input data for one for the 19. Oh, it's the pre-industrial time and the present day, just as York. Yeah, I have my soil NOx emission is directly calculated using the CLM. I add this parameterization to the CLM. This is calculated by the ratios with the nitrous oxide emission in the CLM. It's really different from geochem, but their total value and the spatial distribution. This is the geochem simulated, original geochem simulated soil NOx emission, and this is the soil NOx emission simulated by the CLM. They show spatial similarity, and the total value are also in the same range, but they are really different.
Okay, great, thank you.
Thank you.
All right, I guess we have our poster presentation, so if everybody could come on up. Are you going to drive the computers? Great.
first? Yeah. It's hot.
Do you want a pointer?
So might have a few seconds to point to something.
It's not mine.
It's not you? No.
It's 820. No, that's not.
All right. Okay, so to the standard resistance and series parameterization for NO2 in GeosChem for dry deposition, we've updated this in two ways. First, by implementing hydrolysis of NO2 on the ground surface, yielding absorbed nitric acid and evolved tono. Second, by reconciling near-surface emissions of NOx with grid box resolved concentrations. We do this by discretizing RA. The net effect is shown for particulate nitrate here over the US. If you don't care about that, you might wish to see how HONO changes.
NEI 2011 version ED or EK, the name might make you think they are the same, but trust me, NEI ED needed an update. Emissions from oil and gas didn't look right. And version EK includes improvements over production lands. Also, new compounds were explicitly added, making the lump species don't look so crowded. My poster is B24, so come see me and I'll tell you more.
Hey guys, I've been working on a snazzy new source apportionment tool to be incorporated into GeosChem, and while I was doing that, I found some interesting things about how dust is transported around from the Sahara. If you want to learn more either about dust from the Sahara or the thing that I'm building for GeosChem, feel free to find my poster.
Okay, agricultural waste burning, the day-to-day variability is a big problem for air quality forecast. And we use the neural network to actually predict fire from agricultural burning emissions and significantly improved air quality forecast. And this also opens up a new interactive pathway for air quality and meteorology.
Hi, we developed a 35-year North American fire emission database using the fire report data and the ground-based field load. Compared with GFAT, our compilation named NAFAT shows higher airborne and fire emissions in North America. And using the GeoScan, we found that NAFAT can better capture the fire pollution.
Hi, I'm Eric Luch from the University of Toronto, and I'll be presenting some comparisons of ground-based Fourier transform infrared spectroscopic measurements to the GeoSchem model. So the period I'm looking at is the July and August 2014, and during this time there's these huge fires in the Northwest Territories, and we detected enhancements of CO, ethane, and ammonia in the north at Eureka, Nunavut, and Toronto during this time. So I'm presenting some preliminary comparisons between the model and ground-based measurements.
Hello, I'm Juliet from Colorado State University. The chemical evolution of the plume and its transport pathways are both sensitive to the injection altitude. However, the GeoSchem standard model emit all the biomass burning emissions into the boundary layer. So we develop a new global 3D biomass burning injection height scheme for GeoSchem. This scheme could emit more than 60% of biomass burning emissions above the boundary layer. Are you curious about the effect? Please stop by my poster.
All right, let's thank all the speakers. I think before we depart, Danielle has some.
Yeah, as usual. A few announcements, just what's happening next. So we have a break. We have the working group, three working groups who are going to meet. We have the aerosols working group, which is going to meet from 4:45 to 6, and that's in Pierce 301. That's a building next door. And then the carbon cycle and transport working groups are going to meet jointly in Maxwell Dworkin 119, which is just upstairs. Just take the stairs up, and you'll be there. 6 o'clock to 8 o'clock is our poster session. We'll have food and drink getting wheeled out around 6 o'clock. Again, a reminder to the poster presenters, please take down your poster when you leave so that the poster presenters for tomorrow can put up their posters first thing in the morning. Thank you very much, and see you later this evening.
So we